All right, in the last video, I set up this particular problem. You can see my terrible picture on the upper left here. Maybe if I can move my mouse. Okay, angle of the ramp, mu of the surface, the displacement that it says along the ramp, like that 400 meters, which is like a quarter of a mile, which is ridiculous. But yeah, it tells you the angle of the ramp, the mu value. It starts at initial velocity of 0. Mass of the, that's kind of hard to see, rocket should be 2100. And it said when it was up in the air, it's going to run into a bird dragon thing, which I've labeled as massive dragon, 400 kilograms. And it's moving 8 meters per second to the left. Then we did a force diagram right down here. Friction's back. We can see that because of mu, force normal. The surface is pushing away, Earth's pulling it straight down. And the force applied is pulling straight up there. And we want to know what is the velocity 2.5 seconds after leaving spot B. So this is just going to be for part A. Obviously, part A is going to feed into B and C and D, but yeah, there we go. So first thing that I'm going to notice is that I have an initial velocity and I have a displacement in a straight line path. I need to right now figure out what's the velocity at B. Ultimately, I want to know 2.5 seconds after B, but I'm probably going to want to know that first. You can see that as it's in the air, it's going to be in projectile motion, assuming we miss the bird, which the problem says that we do. Meaning the only thing acting on it is force gravity, so we got a 2D problem up there. But in order to get to that 2D problem, I got to know this velocity right here. Now I'm close to a, excuse me, a one-dimensional kinematics problem. The only thing I'm missing is acceleration, which I got a bunch of forces right here, so I'm going to go ahead and find that acceleration. Since it is angled, I'm going to go ahead and shift the axis by drawing a dotted line down kind of here perpendicular to the surface. And we can see that this angle, we've talked about this in the past, is also the same thing as this angle right here. And let's go ahead and sum the forces in the new y-axis. Since we know it's accelerating up parallel to the surface, it should not be accelerating here, so that should be 0. This should be positive, force normal, because that's going up. Neither of the two of these are on the new y-axis, and force of gravity definitely is pointing down on that. So I have negative force gravity in the y, since force gravity is acting in the new y and the new x, and that's equal to 0. So force normal is equal to force gravity in the y, which is, this guy is mg. It's that hypotenuse right there. And since I'm trying to get that part of the triangle, the adjacent side over there, that's force gravity on the y, I need to use cosine. So this is going to be mg cosine of theta. Now I can plug in numbers at any time here. Quite frankly, with these bigger problems, I'm definitely going to be a lot more prone to letting you know, kind of if you're comfortable with it, to plug in the numbers as soon as you want. That being said, if you're a little bit more comfortable leaving it in variables, that would be my personal preference, but that is up to you. So let's go ahead and calculate this real quick. If you were to calculate what force gravity in the y is, go ahead and getting on my calculator, 2100 times 9.8 times the cosine of 17. I was in radians from a previous problem. That's a pretty big number. That is 19,680. Let's just go ahead, 19,700 newtons in the y. Now that's specifically going to help me find force friction, which is mu times force normal, or 0.4 times that 19,700 newtons. So let's go ahead and multiply that out, 0.4. And so I got a friction of 7,872. But once again, I'm just going to go and round that 70 right there. Because of rounding on these particular problems, it might mean that your answers aren't exactly the same as mine. Obviously, if you chose to round differently in that particular problem. The reason I decided to round where I did is I used 3 significant figures up here, so I decided to use 3 significant figures right down there. But I don't really pay that close attention to significant figures in these problems, so we're probably going to get slightly different answers because of that. Now I've summed the forces in the y to get force friction, which is a common thing that we've done in the past. So let's go ahead and sum the forces along the new x. Equals mass times acceleration on the x. Remember that we shifted the axis, so this is my x right here. Okay, so there definitely is acceleration. Now we need to look for the sum of forces. Now there's definitely positive force applied right there. Force normal is not in the new x. Force friction is definitely negative. And this is where a lot of people stop. because they see it very clearly that those two are along that axis, and what they forget is that force gravity right down here is also acting along that new x, and that's in the negative direction, which should make really good sense considering that it is keeping that acceleration from happening. This force applied is, of course, that 20,000 newtons. This force friction is that well, it's negative because of this, but 7,870. And this force gravity in the x, well, it's going to be very similar. Let's go ahead and just do it right down here in the corner. So it's kind of separate. And that's that mg, the hypotenuse, and the x right down here is going to be opposite of the angle, so times the sine of the angle. Now, one thing that I didn't show in this problem, which you absolutely need to in all this, I guess I did it right here, is you need to make sure and show me what numbers are being plugged in here. It seems like when we do these problems that a lot of people do one thing or the other. They put the numbers in and they don't show the original equation, or they show the original equation and they don't plug the numbers in. You need to do both. The only reason I'm not doing it here, I did it in my work, I just am trying to save space. So that's 2100, that's 9.8, that's sine of 17. So this should be 2100 times 9.8 times the sine of 17, 6,017. Oh, I didn't round the same way. That's stupid. 20. Okay. So now we have plus 20,000 newtons minus 7,870 newtons minus 6,020 newtons divided by, this is this mass being divided under here, 2,100 kilograms, to give us an acceleration of 2.91. Now, once again, I want to remind you, this answer, I'm trying to go pretty quick here. I have actually previously calculated my notes, and I might have been a little bit more exact when doing that. So if you use these exact numbers, I don't think it ends up as 2.91. But what can I do with that now? Well, like I said before, I want to know the velocity there. I now know 3 kinematic variables for this section. We know the velocity initial is 0. We know that acceleration is 2.91. And we know the displacement is 400 meters, and we want to know the velocity at the end of that path, or technically, if you wanted to say that's the velocity at B. Okay, so that's velocity final squared equals velocity initial squared plus 2a delta x. Velocity initial is 0, so square root both sides. You get the square root of 2a delta x. Once again, plug in numbers in. 2 times 2.91. Meters per second squared times 400 meters, square root the whole thing. Now, anytime I square root, I always check the plus or minus. What does it make sense? All right, so it's going in a positive direction right here. It's headed in this positive direction, so it would make sense that we're going to get a positive answer. And after all that, you should get 48.2 meters per second. Now, because it's taking off the ramp the way that it is into 2D motion, technically, that speed, I can add a direction to it of at 17 degrees. Now, the last part of this, what is the velocity at 2.5 seconds after B, is straight up a two-dimensional problem. So I'm going to scroll down here. Okay, kind of draw like a new picture here real quick. We have it taking off at, what did I say, 48. Let's see up at the top right corner there. 0.2 meters per second. Let's make it bigger. At an angle of 17 degrees. And the question is, 2.5 seconds after this, what is the velocity? So let's call that C. Let's say it's, I don't know, somewhere over here-ish, question mark, velocity at C. That's not super helpful. Here, we'll say the velocity somewhere over here. That spot C. That's where we want to know the velocity. And we don't know going up or down or whatever. Let's see what we do know. Okay, since this is a two-dimensional problem, probably the first thing it makes sense to do is figure out what is the velocity in the x and what is the velocity in the y. And those are specifically the initials for the next part. So how do I get that? Just basic trig. Velocity initial in the y is going to be 48.2 meters per second sine 17 degrees. And velocity in the x is going to be 48.2 meters per second cosine of 17 degrees. Let's go ahead and calculate those out. I think this guy is 14.1 meters per second y hat. And this guy here is 46.1 meters per second x hat. Now, also in the y, the acceleration is just negative g, because the only thing acting on it up here should be gravity, because we're not considering friction, it's not hitting anything yet. And we know that the time is 2.5 seconds. Now the question is, what is the velocity here? Now we know that the velocity in the x stays the same, which is good, so we already know it's 46.1. We just need to know what the velocity in the y is going to be. Now a quick trick, by the way, to know whether it's going up or down is to take this number here, this is how fast it's supposed to be going in the y, and divide by 9.8, or roughly 10. In other words, that's going to tell me that it's going to take about 1.41 seconds to get to the top. So I'm pretty sure it's going to be going down over here. Now, if you didn't know that, no big deal. You can solve for this pretty easily because we know 3 variables in the y-axis. That's simply going to be velocity final in the y, velocity initial in the y, plus acceleration times time. So 14.1 meters per second plus a negative g times 2.5 seconds tells us after 2.5 seconds it is traveling down. It's actually traveling at negative 10.4 meters per second in the y. Now, like I said, because there's no acceleration in the x, this is going to stay the same. But neither one of those is our final velocity. That would be this right here. So to get that, we're going to take the x and the y, and we're going to do trig again to get that. So I'm going to shortcut this so that we can kind of finish pretty quickly here. But if you have any questions, please let me know. The velocity final is going to be velocity in the x squared, or technically velocity final in the x, but that's not changing, plus velocity final in the y squared, square root, or just Pythagorean theorem. And that final answer should be 47.3 meters per second. Once again, plug your numbers in. I'm just trying to save you some time. Okay? And your angle, and we need an angle because I said velocity and not speed, is the inverse tangent of velocity final in the y, velocity in the x. If you always put the y on top, you're always going to get the angle from the horizontal. So this is at an angle of negative 12.7 degrees, which makes sense. You can see this going down into the fourth quadrant. That is your answer to A. I know, they take a while. I didn't make physics, I'm sorry. Anyway, so that's the end of part A. I'll be back to talk about part B next. If I can turn off the video.